Okay, so going back to acid-base neutralizations, sometimes you can have a neutralization that does not produce water. So I wanted to show you the most common two examples of that, or at least it doesn't produce water initially when you write the double displacement. So, for example, we have hydrochloric acid and Na2S. This is a double displacement, so I'm just going to swap. And so we're going to have H with S. H is +1, S is -2, so we're going to have 2 of those. And we're going to have NaCl, which is a +1 and a -1. I know that dissolves because sodium is always soluble. H2S I'm not so sure about, so I can always go back to my solubility rules and go see what they say. So generally, sulfides, except for group 1 and ammonium, are insoluble. And group 1 doesn't count hydrogen, by the way. We're talking about just the ions there. But H2S is also an acid. So actually, we will count H as part of group 1 for this purpose. So we're going to say that's probably aqueous, like an acid, because it's got an H in the front. It is on our acid chart, I think. Yep. Right there. Okay, so we'll keep H2S as aqueous. It's not just aqueous, though. As it turns out, this will also form a gas that bubbles out and smells terrible. Oh, we need to balance it here. Oh, there. I fixed that. That was close. So the evidence for this reaction will be a little bit of heat generated, but also you're going to get some H2S gas that forms. So you'll see bubbles. This reaction, this is sodium bicarbonate. Sodium bicarbonate is mostly known as baking soda. And the phrase bicarbonate, by the way, is not the IUPAC name. We would normally name this as sodium hydrogen carbonate, which I told you when we learned naming, you don't name it with 3 words, but in this case you do. But mostly no one calls it that. They call it sodium bicarbonate or baking soda. Anyway, same thing here. Your hydrogen ion is going to exchange with your sodium. So then you end up with hydrogen carbonate, which I'm going to write as H2CO3. That is an acid, so it will be aqueous. It's called carbonic acid. This is what makes our sodas fizzy. They don't actually pump CO2 into it. They put carbonic into it, and then that, as we're going to see in a second, will form carbon dioxide. And then the sodium is going to pair up with the sodium chloride. We know that's aqueous. Now, anytime you make carbonic acid as a product, you have to remember this. It's going to decompose. I just said that's where our soda comes from, right? It's going to decompose into water and CO2 because those are more stable than carbonic acid is, right? So hopefully you can see CO. You take one of these out of there, put it with the hydrogens, and you get CO2 and water. So the evidence for this reaction is going to be heat, because when you make water, it gets warm. You'll only notice that if you're actually touching the test tube, though. So if you leave it in your test tube rack, you may not think that the reaction happens. Okay, let us summarize. Things that are soluble, ionic compounds, are strong electrolytes. Things that are insoluble will not carry a charge. They are non-electrolytes. If something is a strong acid or a strong base, they are also strong electrolytes. No tricks there. Weak acids and bases are weak electrolytes, meaning they don't light up a light bulb all the way. They don't produce as much energy. Okay? And so that's good enough. We don't really need to learn about oxidation states yet, except for in terms of making compounds like Na plus and Cl minus. Alright, so the last little bit for this video is about something called Net Ionic Equations, and you need this concept to be successful writing your reactions for experiment 4. Basically, you have to understand what is going to be solid versus aqueous in a double displacement reaction, and you need to understand that when something is an electrolyte, that means it exists as separate ions. We also have a new vocab word for this. It's called spectator ions. Spectator ions are the ones that don't do anything in the reaction. So let's look at some examples. Here we have sulfuric acid and potassium hydroxide. So that's 2 compounds it's going to be a double displacement. Okay, that means my cations are going to switch places, but I have two H pluses to react with, so I know I'm going to make two water because we just learned that a second ago. Water, of course, is a liquid. And then I'm also going to have K and SO4, so that's going to be a K with a +1, has to have two of them. And this will be soluble because potassium is always soluble. I need to have a 2 over here so that it balances out. And that's my balanced reaction, right? So that's my complete balanced reaction. I have to have that in order to get to the net ionic equation, okay? Alrighty, so what we're going to do to make a net ionic equation is first we have to do the complete ionic equation. You can't skip this step or you'll miss things. And that just means anything that is an electrolyte gets broken up. Okay, so here we have an acid, so that's going to break up with hydrogens, in this case 2 of them, so I'll put that in front. They are not connected to each other. They are H pluses that are each connected to the sulfate. So I want to make sure that the subscript becomes a coefficient when I'm doing that, when I'm ionizing things in general, not just for hydrogen. The sulfate ion will be there, and ions are automatically aqueous, so I don't always write it. But if you see a charge, it has to be dissolved in water or it's not stable. KOH is a strong base, so that's a strong electrolyte. So we're going to make sure to distribute the 2 to both pieces, but you're going to end up with 2 K pluses and 2 OH minuses. Water is not an electrolyte here. So we're going to, you can tell because we wrote liquid instead of aqueous. And so we're going to keep it as 2 water. So things that are solid, liquid, or gas stay as they are. This was why we learned about solubility rules. K2SO4 is an ionic material that is soluble. So we're going to end up with 2 K pluses and an SO4 2 minus. So the complete ionic equation shows you what is actually present in your beaker when you do a reaction like this, or your test tube, or whatever. All right. Then, to go from the complete ionic equation to the net ionic equation, we take out anything that doesn't actually participate in the reaction. Those are the spectator ions. So looking at your complete here, we have sulfate on both sides. We're going to take that out. And we have potassium on both sides. So these are called spectator ions. It means that I could literally have any other ion with the same charge, and it would do the same thing. All right, so I could put a carbonate, CO3 2 minus here. I could put, I don't know, anything with a 2 minus charge, and it's going to behave this way. Anything with a 1 plus charge will behave this way. So we can get to the net ionic equation by just writing everything that didn't get canceled, everything that was not a spectator, and do not change the coefficients. Leave them as they are. Ta-da! That's the ionic equation that describes the neutralization between sulfuric acid and potassium hydroxide. I want you to pay attention when you're doing the acids reacting with the bases in experiment 4. Look at the net ionic equations and find the pattern. It's going to make it a lot easier to do a couple of the problems later on in the lab, so keep that in mind. Oh, and in lecture too.